Hey, what's up, guys? I hope this lecture finds you in a healthy well-being. So, as I promised you, today I'm going to share with you the solution for the final exam took place last semester. Okay, before I get started, I just would like to say that I claim no ownership for the material presented here, and these questions were written by those three examiners. Okay, so let's get started. So the first question was to convert two numbers between one numbering systems to another. So the first numbering system was hexadecimal and the second numbering system was octal. So in hexadecimal, if you remember, guys, at module 1, we have explored that each digit in hexadecimal can be represented by 4-bit in binary. As such, for 2 to be written in binary will require 4 bits, which is 0010. F is going to be like 4 ones. And for C, it's 12, so it's 1100. Okay? So if you have any questions, go back and review like module 1. Okay? When it comes to the octal requires 3 bits because the base is equal to 8. 8 can be represented 2 to the power 3. Okay? Therefore, this one can be represented by 3 bits as 001. The 4 digit here can be represented by 3 bits, which are 100. And the 2 can be represented by 3 digits, which are 010. And after the radix points is something similar. So it's going to be 001 and 110. Okay? Now, when it comes to this kind of questions, that questions is something similar to whatever given you like at midterm 2019. And actually, it's much simpler than my question. Okay, guys? So basically, you have two numbers, and these numbers are 10001 and B is 10010. So that's basically, if we're going to convert them, this is like 17 in decimal and 18 in decimal. So the question is asking you to do it, to do the operations to calculate C and D using the ones complement format. Okay, ones, not twos complement. Okay. And they explicitly ask you to use like a 6-bit representation. That's why we're going to add a 0 at the beginning of each operand, okay? And after that, ask you to represent the decimal number, this decimal number in BCD and XS3. So each, okay, I'm gonna go ahead and reveal the solution. So these, in order to represent the following number using a 6-bit representation, we're gonna add 0 here and 0 here. Okay, so this can be, verified as 17 in decimal and 18 in decimal. So in order to calculate C plus, in order to calculate C, it is basically A plus B. So we're gonna add each bit from A to the corresponding bit from B, and so on to calculate it. So after we do the addition, we notice that the most significant bit is equal to 1. That means an overflow has happened, okay? And the results is equal to minus 28, okay? Now, if you would like to find A minus B, which is 17 minus 18, which should give you minus 1, okay? So A minus B is equal to A plus the ones complement of minus B, okay? So how are we going to do that, okay? We're going to convert the B, okay, using the ones complement notation, okay, guys? And after that, we're going to add A to B, okay? So the result will be equal to 1, 1, 1, 1, 1, 0. So we have 1, so the result is in negative. That means in order to find the correct magnitude, we need to complement it again using ones complement, okay? So in order to do so, we're going to, flip each bit because it's a ones complement. And we're going to get 1, 0, 0, 0, 0, 0, which is what minus 1. That means that both results, they go together, and this is minus 1, which represent the correct answer. Okay, so when it comes to representing this decimal number, okay, in BCD, so each decimal number requires 4-bit to be represented and encoded in binary for BCD. So the 6 here can be represented using 01110, and the 3 here can be represented by 0011, and 2 can be represented by 0010, and the 8 can be represented by 1000. Okay, in order to, to calculate the equivalence in XS3 code, the XS3 code has been given in my course at module 4.1. Okay, guys. So basically, what you need to do is, at this type of code, is to add 3 to each equivalent code in BCD. So if we're gonna add 3 to 6, it's gonna be 9. That's why I put 9. If you're gonna add 3 to 3, it's gonna be 6. 3 to 2 is gonna be 5, and 3 to 8 is gonna be what? It's gonna be 12. 12 is equal to what, guys? No, it's gonna be 11. Sorry, 11 is equal to 1011. Okay, guys. Another way to solve it is to add the decimal equivalent to 3333 and convert the result directly to what? To hexadecimal. Okay, so the result will be in hexadecimal. So if we add 8 to 3, it's going to be B. Okay, because it's 11, it's going to be B. Okay, and then 3 to 2 is going to be 5, 6, 9. And then after that, encode each digit using 4-bit from hexadecimal to binary. Okay, so the 9 is going to be 1001, 6 is going to be 0110, and 5 is going to be 010, and B is going to be 1011. This approach is, is dangerous except when you're going to reach, okay, in X3, the maximum number that can be represented using one digit is what? Is 9. 9 in BCD plus 3, which is 9 plus 3, which is equal to 12. So the maximum one is going to be C. Okay, so if you're gonna get D, so D you need what? You need to split them into 2 4-bits. Okay, guys. Now this question 2. So you have this Boolean representation, and you're asked to implement it using exclusive OR and gates. So if you have noticed that AB prime is the common factor with this one, and A prime B is the common factor with this one. So if we take AB prime as well as A prime B, we're gonna get this, and that's basically is what? An XOR between C and D. Okay, so if I take C XOR D as a common factor, I'm gonna get an XOR between A and B. So the resultant will be A XOR B ANDed with C XOR D. So that's the first part. Now you have this questions, and this questions require you to just to think, a little bit, and actually you can find the solution on the internet for this question. Okay, guys. So remember, guys, if you remember the implementation of a half adder, any half adder, okay, half adder. If you go to module 4.1, the half adder has X and Y, and has the sum and the carry out. And the sum function was equal to X XOR Y, and the carry out was equal to X and Y all the time. So if I connect here A and B, so what will be F here? F is going to be basically A XOR B, and the carry out, let's name it M. M is going to be like A and B, okay? So basically, to implement A XOR B XOR C, what you're going to do, guys, is you're going to ripple, like, 2 full adders at the same time. So this will give you A XOR with B, and this at this one, between these 2 operands, it's gonna be like what? This sum is gonna be A XOR B XOR C. Now, in order to implement A, this one E, which is A prime BC plus AB prime C, that is equal, if I take C as a common factor, A XOR with B with C. So basically, guys, that means that I'm gonna AND C with the sum from the first full adder, and that's why I needed to connect it here. Okay, so that is how I'm gonna do it. Now, when it comes to, because this is A XOR B, okay, and this is AB, okay. Now, when it comes to this one, guys, this is according to De Morgan, can be represented as AB prime, okay, C, and is added to A, B, C prime. So that is basically an XOR between A, B, and C, okay. So to do it, we need this one as the first operand, and to XOR it with C, and this C as the second operand. So that's basically what's happening here, okay, guys. Okay, that is for F. And if you're gonna find G, which is ABC, that's basically, remember that is AB, that the carry out, and that is the second operand A, B, and we have C. So the carry here is going to be an and between those two, which are A, B, C. Okay. Now let's take a look at the question 2 part B. So a 4-input majority circuit is a combinational circuit whose output M is equal to 1 if the number of ones in the input variables is odd. Okay, so this one is a little bit tricky, so you need to pay attention. If the number of ones in the input variables is odd, that means if the code at the midterm has an odd number of ones, the output M will be 1. Otherwise, the output will be 0. So build the truth table. So look at this. So when we have 0, 0, 0, we have no ones. So I'm going to put 0. Now at 0, 0, 1, I have 1, and it's an odd one because I only have just 1, and I have 3 zeros. That's why I'm going to put 1. At 2, I have an odd one because 0, 0, 1, 0, and it's only 1. So I'm going to put 1. At 3, I have even number of ones. So I'm going to put 0. At 4, it's going to be odd. At 5, it's going to be even. That's why I put 0. At 6, it's going to be even. I'm going to put 0. At 7, I have 3 ones. So it's odd. That's why I'm going to put 1. And so on. Okay, guys? So simplify the function M in as its sum of product using K-map. So I'm not going to re-explain it. It's going to be easy. Or you can go here. That is sum of products. So M is equal to 1 at 1, at 2, at what else? Let's see, at 4, at 7, okay, and then at, look at this, at 8, then at 11, and then at 13, and at 15, okay? So M is going to be just the sum of product of 1, 2, 4, 7, 8, 11, 13, and 15. If you're gonna write it, it's gonna be like, the only way to simplify it is using an XOR between all the operands. Okay, that's the only way to implement it. So it's gonna be A XOR with B, XOR with C, XOR with D. Okay, so draw the logic circuit by using 8 to 1 multiplexer. So even though we have 4 bits, and 4 bits requires, 4 bits requires like a 16 to 1 multiplexer. We the question is asking you to use 8 to 1 multiplexer. So we have to find a relationship between the least significant bit D as well as the output. Okay, and use A, B, C as the most significant, as the selection bit. Okay, that's what we did here. Okay, so let's take a look here. So so we're gonna group these. Okay, and we're gonna group these. We're gonna group these, and we're gonna group these, and we're gonna group these. And we're going to group this, and we're going to group this, and then we're going to have like these two. Because that's, guys, this is 0, 0, 0, and still here, it's 0, 0, 0. And we need to find the relationship between these two. So that's equal to D, okay? That's why at 0, input 0, I put D. Now at 2, this is like, look at this, 0, 0, 1, 0, 0, 1, okay? So these two, they share the same code, so they have the same selection. Okay, and look, it was 0, 1, it becomes 1, 0, so that's D prime. Okay, that's why I put D prime here. Now here, at 0, 1, 0 for ABC, 0, 1, 0 for ABC, it's still like, if D was 0, 1, and M is 1, 0, so it's D prime again. So that's why I put D prime again. And guys, it's so on. At 7, look what will happen. 7, okay, here, which is, here I have what? 0, 1, 1, and 0, 1, 1 here. Okay, so these two, look at them. Okay, so D is following M at all times, so that's why it's D. So look at this, when I put at 3, because this is 0, 1, 1 can be coded as a 3, so that's why I put D. Okay, and so on. So this is the way that to solve this question. Okay, guys, and this is given at module 4, the last lecture. Okay, so guys, here, like, I received an email from the student and he asking me where is the table, but actually you don't need the table. Okay, so they told you have here an 8 to 1 multiplexer. So you basically, guys, you're gonna have here the selection here, S2, S1, and S0 as A, B, and C, and you have here F. Okay, and here you have 0, 1, 2, 3, 4, 5, okay, 6 and 7. So what they are saying that at I2 and I0 and I1 and I2 is equal to 0. So I1 and I2 is equal to 0. What does that mean? You need to group them. So this is here, okay, is equal to like I1 and I2. Sorry, I1 and I2. So I1 and I2, look to the brown here. So that represent, guys, what? I1, okay, and at all time, because I just have like, I can group them, okay, like I need to find in terms of D, okay, because it's written here in terms of D. So at I1, this is I1, and as well as at I2, so this is I2 because this is 0, 1, 0. And remember, I'm gonna find it in terms of what? Of D. So I1 and I2, like it's equal to 0. That means what? That means this is the way that I should write it, okay? So that is equal to 0, that's equal to 0. Now, when I3 and I7 equal to 1, you need to build this table, guys. I3 and I7 is equal to 1. What does that mean? That means, okay, look at this. That I7, it's going to be like 0, 1, 1, 0, as well as 0, 1, 1, 1. Okay, and this will give you what? Like, two values of D. So if it's 0, 0, and if it's what? And this if it will give you 0 and 1, and this will give you two value of D, which is 0 and 1. So that means, guys, look at this. At 3, that is 3, sorry, 0, 0. Okay, so let me do it again. So we have it encoded in terms of A, B, C. So I3 is 0, 1, 1. So the value of the, regardless of it's 0 or 1, okay, that is A, B, and C, and this is D. The value of F is equal to what? Is equal to 1. And same thing, if it's 1, 1, 1, regardless of the value of 0 and the value of what? Of D. If it's 0 or 1, F is equal to 1. So what kind of minterms this will give you? This will give you 0, 1, 1, 0, which is what? 6. And 0, 1, 1, 1, which is 7. Okay, so look at this. At 0, look at 6 and 7, F is equal to 1. As well as at 14, 1, 1, 1, 0, 14, and 15, 1, 1, 1, 1, it's equal to 1. That's why F is equal to 1. This is the blue. And similarly, we apply the same approach. I4 equal to I5 equal to D, and I0 is equal to I6 and equal to D. So similarly, like, when you have 1, 0, 0, regardless of that is A and B and C, regardless of the value of D, if it's 0 and 1, F is equal to 0 and F is equal to 1. So if what does that mean? That means you're going to have a minterm when D is equal to 1. That's it. So the minterm is going to be 1, 0, 0, 1. So that's 9. Okay? So as well as we do the same thing when it comes to 5. Okay? So it's going to be at 1, 1, at 1, 0, 1. It's going to follow D. So if D is equal to 1, that means this will be equal to 11. And at 11, F will equal to 1. So if we're going to build this table, guys, okay, look at this. So D was equal to 1 here, and here, and here, okay, as well as here, as well as here, and here, here, and here. So what are the minterm? What are the, like how we can write this function in terms of sum of product? It was at 1, okay, this is 1, and it was at, look at this, guys, it was at 6, as well as 7, because F is equal to 1, then 9, 11, 13, 14, and 15. Okay, guys? So that is the way to solve this type of a question. Okay, now, guys, here it asks you, given this, and this is again at module 4. Three. You can find the explanation of the decoder here. So you have this function, and this function is written in as a sum of a product, okay? And we would like to implement this function using external and gates only. So what we need to do is to write it in terms of product of sum. So what are we missing here? We're missing 1 and 6, okay, in terms of a max term. So what we have to do, guys, is to implement this decoder as an active low decoder when it comes to the output. So it's complemented. And after that, what you have to do is, something like, just take 1 and 6 and them, and that's it. Boom. You're going to have this decoder implemented. Now, let's take a look at this example. So they ask you to design a module 12 asynchronous up counter. So it's a ripple. It's something you're going to find it at the ripple counter, like explained at the DGD, like 6. Ripple counters using the negative edge trigger JK flip-flop. So the asynchronous or the ripple counters is implemented in such a way that the clock at the synchronous counter, the clock is shared among all flip-flops, okay? In the asynchronous or the ripple counters, the output of the first flip-flop will serve as the clock for the next flip-flop, and so on, okay? So if it's module 12, so what does that mean? You need 12 can be encoded as 1100. So as you need 4 flip-flop for each to represent each bit, okay? So 4 JK flip-flop, okay guys? So the way to implement it is we gonna ripple the output from each flip-flop, okay, to serve as a negative edge triggering for the second flip-flop, okay? You see the bubble? And we have to stop when we have the last 2 most significant bit equal to 1. So what does that mean? That means we take here, like this is Q2, if we encode it as Q3, Q2, Q1, and Q0. If those are equal to 1, I need to use a clear, okay, and send a signal to reset all the counters. That's why I need to take both of them, NAND them, to get what? An active low clear, and send it to all flip-flops. So once this counter will increment sequentially until I reach what? 1100. At that point, after that negative edge triggering, what does that mean? This signal will become what? Activated, okay? So it's gonna give me the 1 with 1. So NAND it together, this will give you 0. 0 means all this is 0, 0, 0, and 0. All this will reset, okay? So that's why, okay guys, this circuit has what? This circuit will stop until you reach 11, and that's it, okay guys? If state 11 will be counted at state 12, no, it will not be counted because this circuit will reset, okay? Now, okay, what is the maximum modulus of this counter? So let's suppose that you don't have this control enable signal, okay? That circuit can count because you have 4 flip-flop to 16. But even if you answer 12 to me, I'm going to still consider it right. Okay, so this circuit, guys, is something similar to what we covered at lecture 6.2, or this question. Okay, so you are giving the input of the flip-flop, okay? So, and you need to design it in such a way that A is the most significant bit and D is the least significant bit. So what you need to do, guys, so you need to encode A, B, C, D as your input. So 0, 1, 0, 1, 0, 1, 0, 1 as the present state. And now you have to go and look, the excitation table is already is already given to you. So this T input is already given to you. So if you have 0, and T of A is equal to 0, what will be the next state? The next state should stay the same. If you have 0 here and 0 here, what will be the next state? Should be 0, okay? Because, the T is equal to 0, no change. And if you have 0 here and you have at the present state and TC is equal to 0, it's going to be what? No change. If you have 0 here and you have 1 here, you have to write 1, okay? Because TD will flip, this input will toggle the present state to become 1. And if you do the same thing, you're going to get this next state table. So if you are at 0, 0, 0, the next state will be 1. That's it, what we're going to do. And this is increment by 1. Okay, guys? That is this questions, and you're going to get, you're getting 10 points at that one. Okay, now this is the last questions, and you have to read between the lines. So they give you like T0 is connected, and they want you to find the connection of T1, T2, and T3, and they even told you how to do it. And look at this. This is like a positive edge triggering, okay? Synchronous counter, okay? So using AND gate, design logic, a logic counter, okay? It's counter missing here. Their question that at the positive edge F1 flip 1 means change the state when Q0 equal to 1. So what does that mean? You need to find, you need to connect that here. And then, and FF2 change the state when Q0, Q1 equal to 1. So you need, like, for this one, it's an AND gate, guys, between what? Between Q0 and Q1. Okay? So that is for FF2. And FF3, it's an AND gate between all three of them. So you have Q0, Q1, and Q2. AND gate between all of them together. Or what you have to do is, since you already implemented this, so this AND gate can be just, an AND between this one, as well as the loop back from Q2. Okay? And this is how we can do it. Okay, guys? Now, let me share the solution with you. So that's it. So look, let's read it again. So Q0 will change state, F1 will change state based on Q0. So I'm going to connect it to T1. Okay? Q0, Q1, if it's equal to 1, FF2 should change the state. What does that mean? That T2 should be equal, T2 should equal to what? To the AND between Q0 and Q1. And that's why I have, like a T2 is an AND between what? Q1 and what? And Q0. Okay? As you can see, guys. And flip-flop 3 change the states when you have Q0, Q1, and Q2 equal to 1. That means what? An AND gate between, that is, guys, what is, remember, that is Q1 and Q2. And this is what? Q2. Q1 and Q0, sorry, and this is Q2. So that is T3. Okay, so let's take a look at this. What is the function of this circuit if T0 is equal to 1? So if T0 is equal to T0 here, that T0 is equal to 1, that means this bit will be at the next positive edge triggering, this bit will be flipped, and this will become 1. And this one will go and flip this, this one will become 1. So at the second positive edge triggering, this one will become 1 again. So, okay, so you are at 0, 0, 0, 0, and then it will become 0, 0, 1. And after that, this one, okay, this one will flip it. So it's going to be what? An increment 1. So 0, 0, 1, 0, okay. And after that, this one will work as long as both of them are equal to 1. So if I have 0, 0, 1, 1, then this one will start working and sending me like results to the other one. So in other words, it's going to be an increment. It's an up counter, okay? And the circuit will increment by 1, okay? If T0 is equal to 1.
Bottom line, when T0 is equal to 1, this circuit represents an up counter. So if we assume that the initial state is 0, 0, 0, 0, so after each positive edge transition, the states goes up by 1 until we reach 1, 1, 1, 1, which is 15, and then go back to 0, 0, 0, to state 0. When T0 is equal to 0, if the initial state is even like 0 or 2 or 4, etc., then no change in the circuit when the flip-flops are triggered. Why? Because as you can see, the input for each flip-flop requires an AND operation with the previous flip-flop states. However, if the initial state is odd, like 1, 3, 5, then the states goes up by 2 until 15 and then goes back to 1. You can try it yourself, guys, by building a state table at which you assume that you're going to start by T0 is equal to 0 and then find the relationship for each equation, okay, because you have them. So T0 is equal to 0 and T1 is equal to an AND gate between T0 and T1, and our T1 is equal to T0, as well as T2 will be an AND gate between T1 as well as what, guys? T0, and so on. Okay, so what is the modulus of this counter? So if t0 is equal to 1, then it's an increment by 1. It's an up counter, a fully sequenced up counter with the modulus of 16 because it's from 0 to 15. However, if t0 is equal to 0, then it's a modulus of 1 in case you have an even state because you're gonna like reset back to 0 just like in one transition, or you're gonna like you're gonna increment by 2, so you're gonna divide that modulus 16 by 2, which is 8. Okay, what is the maximum modulus of this counter? So the maximum modulus of this counter will be, guys, like 16 for both t0 is equal to 0 or t0 is equal to 1. Okay, I hope this is clear for you guys. And for the other sample exam, it's nothing more than like the exercises or the problems at your textbook. Go ahead and practice it. This will be the last video I'm gonna like post it at this class, and you need to solidify your understanding by watching the lectures, solving the other sample exam. Okay, and I wish you good luck in all of your studies. Okay, have a nice day.